Yes, sir.
Okay.
Sir,
Good
please
afternoon.
start. Recording started. Yeah.
Okay. Thank you, sir. Good afternoon to our respected principal, sir, Professor Gyantos Kumar Jha, sir, IQAC coordinator and webinar committee convener, Dr. Vinita Tuli ma'am, esteemed guest speaker, Dr. Ajit Kumar, sir, teacher in charge of Department of Mathematics, Mr. Kapil Kumar, assistant in charge of Mathematics Department, Mr. Rajkumar Bhagat, sir, faculty members, students, and dear participants. I, Anil Kumar Razak, on behalf of Department of Mathematics, ARSD College, welcome you all for the national webinar on application of linear algebra to the machine learning and artificial intelligence, organized under the aegis of Internal Quality Assurance Cell and Department of Mathematics. Strong leadership is the foundation of any institution's success. ARSD College has reached new height of success under the able guidance of our Honorable Principal, Sir Professor Gyantos Kumar Jha. In your dynamic leadership, ARSD College has achieved All India Rank 7th in NIRF 2022. Thank you, sir, for your support, encouragement, and for giving us this excellent opportunity to organize such national webinars for the benefit of faculty and students. It is my honor and immense pleasure to introduce our guest speaker for today's webinar, Dr. Ajit Kumar. Dr. Ajit Kumar is working as an associate professor and head of Department of Mathematics, Institute of Chemical Technology, Mumbai. He received a PhD degree in mathematics from University of Mumbai in the broad area of differential geometry. He was NBHM Research Fellow during his PhD. In previous appointments, he was assistant professor in mathematical sciences foundations at St. Stephen's College, Delhi, and lecturer at St. Xavier College, Mumbai. His current research interests include optimization techniques, data analysis, and mathematical pedagogy. Dr. Ajit Kumar have guided 2 students for PhD and 15 master's projects. He has authored more than 13 research papers published in journals and proceedings. He has authored 5 books, namely Group Theory and Expedition with SegMath, a foundation course in mathematics, a basic course in real analysis, calculus with SegMath, and linear algebra with Seg. Dr. Kumar has delivered several invited talks at national and international level. He has conducted several workshops and conferences for teachers and students over the years. He also has expertise in several mathematical softwares like SegMath, Python, R, Mathematica, GeoGebra, Scilab, etc., and have given several courses using this software, and also had designed curriculum using them. He is managing trustee of MTTS Trust since 2016. He is member of the National Core Committee of the MTTS and PTMT. He have been part of designing syllabus of many courses and have been member of board of studies of many institutions. We take this opportunity to thank him and we welcome you again, sir. Dear participants, at the end of the lecture, we have some time of question and answers. If you wish to ask questions, you can write your questions in the chat box. We'll enable chat box at 5:10 p.m. So now to start this session, I invite our respected guest speaker, Dr. Ajit Kumar sir, who will be discussing on the topic applications of linear algebra to machine learning and artificial intelligence. Dr. Ajit sir, over to you.
अनिल सर ने ज्वाइन कर लिया है.
Yes, yes. So now I invite our respected honorable principal sir, Professor Gyantos Kumar Jha, to welcome our guest speaker and say few words, sir.
Thank you, Anil. Thank you. Respected guest speaker of this webinar, Mr. Anil Kumar Rajak, Dr. Preeti Jain, Mr. Rajkumar Bhagat, and other colleagues of the mathematics department. I'm very glad that you are organizing this kind of workshop and webinar for the benefit of students. And I'm very thankful to our guest speaker who has given his valuable time to deliver his lecture in this evening. And I'm sure that our student and faculty will be benefited from his lecture. So thank you so much, sir, for giving your precious time for all of us. And once again, I welcome you all. My best wishes to organizers and especially to Mr. Anil Kumar Raja. Thank you. Over to Anil. Thank you, Anil.
Thank you so much, sir, for your motivational and encouraging words. It means a lot to us. Thank you so much, sir. Now I invite Dr. Ajit Kumar, sir, to start this session. Over to you, sir.
Okay, thank you. Thank you very much, Professor Anil. First, let me thank the principal of ARSD College and the Department of Mathematics, Chairman of IQSC, and all the organizing committee members for organizing this lecture. I'm really delighted to give this lecture. So let me just first share my screen. Is my screen visible?
Yes, sir.
Okay. Yeah. So the topic of today's lecture is, as it was mentioned, applications of linear algebra to machine learning and artificial intelligence. This is a kind of buzzword these days, and I'm sure all of you keep hearing this. I'm sure many of you must be already using this. If you just try to Google this machine learning, artificial intelligence, you'll get possibly a few million web pages having this the keyword. And it's becoming extremely popular in this age of what do you say, digital world. So what I'm going to do today is, first of all, I'll just briefly tell you about machine learning, artificial intelligence. Then we will look at some of the concepts that we study in linear algebra and how they are used in some of the applications in machine learning. That is what I'm going to do. So I'll possibly give you maybe 4 to 5 applications, and applications of some very simple concept that we learn in linear algebra. I think there are a lot of students attending this, including some teachers. So of course, for many teachers, this may be very, very simple one, but students, I'm sure they may not have seen all these things that I'm going to talk about. I'm also going to kind of demonstrate some of these concepts using a software called Sage Math, which is what I have shared at present. It works, it's a free and open source software. And I will also maybe use a worksheet from Python. Actually, Sage Math is a Python-based free and open source software. So if in case any of you are interested to learn about Sage Math, you can look into its website, sagemath.org. Right, so let us very briefly look at what is, by the way, at any stage, if anybody has any question, you can raise your hand and then ask. I hope you will be able to do that. Or of course, at the end, we can look into any query that you have. But I would prefer, in case in between, if you have any question, you can let me know. Yeah, so broadly speaking, this machine learning, artificial intelligence, actually both are fields coming from computer science, and they are very, very closely related to each other. In fact, this machine learning can be thought of as a subfield of artificial intelligence. These days, you also hear not just machine learning, but also something called deep learning. That's a, can think of subfield of machine learning. So artificial intelligence, actually, as I said, it's a field of computer science, and it tries to mimic human intelligence. That's a really tough one, right, to mimic, because we know that this brain is very, very complicated kind of thing, which is very difficult to kind of simulate this. But yeah, this artificial intelligence, that's the philosophy behind it. So it actually focuses on writing computer programming and algorithms. If you look at, for example, the AlphaGo, they developed this as artificial intelligence program, and which actually defeated world champion in Go. There is a game, Chinese game called Go. Also, I think it they have developed computer program to where computer can play chess, right? Chess and Go and all these things, etc. So this actually, I mean, you can think of that as a program that really kind of it's a kind of another player, right? But it is computer who is playing. So that's mimicking this actually somebody's brain in some sense, right? Okay, and this machine learning actually enables computer system to decide or predict based on some data or historical data, and it actually uses high-level mathematics and statistics. And linear algebra is actually one of the key component of machine learning and artificial intelligence. So somebody having very good background in linear algebra, calculus, optimization will definitely have an edge when they want to use machine learning, artificial intelligence algorithms. So let me just start with very, very simple question, right? What do we study in linear algebra? What are the basic objects that we deal with in linear algebra? If you have any answer, you can unmute and ask. You tell me. In case you have any answer, you can just unmute and tell me. I'm not sure whether participants.
Actually, participants are not allowed to unmute themselves.
Okay. Then okay, fine. Let me just go over it. Then at the end, if they have questions, please note down your questions. And then generally, I prefer to be more interactive during the online lecture also. Otherwise, it becomes really somewhat boring. But anyway, that's how it is. So let's continue with this. Yeah. So basically, in linear algebra, the main or the basic objects that we deal with are vectors and matrices, right? So we play with this object, vector space. The elements of vector space we also call as vector, right? And the matrix can be thought of as column of vectors. But actually, for me, any data is a matrix. If vector for me is one-dimensional data, whereas matrix will be multi-dimensional data. So as I said, when we this machine learning is all about dealing with data, machine learning from the data and giving some kind of inference. So if I want to deal with data, whether the data is actual numerical data or it could be data coming from images, image is also a data, can be thought of as a matrix, you'll see in a minute, or it is a video, or it's a text, speech, anything, all these things are data. So if I want to do any analysis, if I want to analyze this data, that is nothing but working with matrices. And if it is one-dimensional data, that's a vector. So if I want to analyze this, the data, that means we have to deal with vectors and matrices. That means we we require notion of linear algebra, right? So linear algebra plays very important role in all these algorithms. So for example, if I just look at, let us import data. I just yesterday only downloaded this stock exchange data of Nifty 50, which is a basket of 50 top 50 companies listed in National Stock Exchange. So I'm reading this data. This data is 1 year everyday prices, right? So it has about 162 rows and 7 columns. So each row, each column, I can think of as a vector, whereas this entire 162 by 7 can be thought of as a matrix. So like that, if you have any data that is nothing but a matrix or list of vectors, right? So if you look at this, what is this data? This data is, this is the date-wise opening price, high price, low price, closing price, and adjusted closing price, and the number of stocks it traded, right? So it has these 7 columns. So each column can be thought of, each column except the date, you can think of as a vector, right? So for example, if I look at a vector in R3, usually you write that as AI plus BJ plus CK, right? But that is nothing but ABC, or a column vector ABC, right? So if I have n-dimensional data, this is nothing but, let us say this vector is x1, x2, xn. A vector in Rn, generally it is x times e1 plus x1 times e1 plus x2 times e2 and so on. So this is how we think of any data as a vector, right? So as I said, when we want to analyze this data, we need concept from linear algebra. These are the last few data, last 5 data here. And maybe we can store this data, and we can, let me just, for example, look at the every day, what is the movement of the stock, right? So that is nothing but opening price, closing price minus opening price. So you will get a set of 162 numbers. All are between, some are negative, some are positive. Negative means that the price fell down from the opening price, right? So that's it. This is a vector which is sitting in R to the power 161, right? 161 dimensional Euclidean space, right? So if I want to deal with this, the vector notion will be required. So let us just also plot this data. If I plot this stock movement, this is how you can see here. So for example, you can see here it was minus 3, and the next day it went up to positive. So there is a lot of movement from this to this, right? So this just, and you can do various other visualization about this data, right? So as I said, basically any data for me is going to be either a vector or a matrix. If it is one-dimensional array, we'll think of that as a vector. If it is a multi-dimensional array, we'll think of that as a matrix. That is what we are going to deal with, right? So let us move on. And then if you look at, for example, any image, that also is nothing but a matrix. So let me just show you how you can think of that as a matrix. In fact, let us look at this picture. This is a statue of unity of Sardar Vallabhbhai Patel. I have imported this data in Python and plotted, right? Now I can read that as a matrix. So I can make this as a matrix. So you can see here, this is actually 3-dimensional array. This is 3-dimensional array, and size of this matrix is 995 by 1770 times 3. So that is why it is 3-dimensional array. Any actually color image is a 3-dimensional array. And in case the image is of very, very high quality, then the size of the matrix will also become larger. So the better is the quality of the image, larger will be its size. So if I want to deal with any object or any image processing, which is a very, very, what you say, an important task in artificial intelligence and machine learning, especially in medical field. There are a lot of analysis which are done from the medical images, and based on that, they make conclusion whether somebody is likely to have certain disease or something. For example, in cancer, a lot of researches are going on, right? So, but then the other thing, if you look at, for example, image processing itself, if all of you must have seen this Adobe Photoshop, right? So that, what is it? Actually, it just uses very simple concept of linear algebra, like linear transformation. I'll show you that. And just by using these things, you see Adobe Shop, that's a proprietary software. They have made millions of rupees, right? This was introduced, I think it was invented by actually one PhD student along with his brother, Thomas and John Knoll in 1987. And since then, you can imagine how much money they would have made. Of course, they would have kind of changed the algorithms and other things, etc. But all these images processing is nothing but a very simple concept of linear transformation. Okay, I'll show you how it works in a minute. But that's an application of linear transformation that we learn in linear algebra class. Any linear algebra course, you will have a chapter on linear transformation, how to write, what is meaning of linear transformation, how to write linear transformation from finite dimensional vector space to finite dimensional vector space as a matrix and things like that, right? So we look at application of that. Similarly, the other concept that some of the concept that you learn in linear algebra, like eigenvalues, eigenvectors, we look at some application of that. You also learn inner product space. In that, you also learn what is called orthogonal projection, or simple matrix multiplication also has a lot of applications. So we will look at some of these applications, right? So as I said, this any image is nothing but a matrix, and that is how you can think of. In fact, if you can convert matrix, convert an image into what is called grayscale image, gray image, and that will become actually two-dimensional array. So you can see here, this is a grayscale image. The same image I have converted into grayscale using inbuilt function called convert. And if you look at the dimension of this image, this is two-dimensional, and the shape of this is nothing but 995 times 1770. Okay, so that's a matrix. Any gray image is going to be two-dimensional matrix, and color image is going to be three-dimensional matrix, right? So as I said, any image processing that we want to deal with, actually it is just dealing with the matrix associated to this, and that's where linear algebra comes into picture, right? So, and once you have a matrix, so this is the matrix. This is the matrix. You can even plot that matrix. You can plot the matrix, right? So using matrix plot, you can see here, of course, the quality somewhat, the algorithm that it uses for this plotting, and this may be slightly differ because each algorithm, there will be some kind of loss of information. So this from Sage Math, I'm using matrix plot. It is able to plot, but the quality is not all that great. But in any case, what I mean is, if you have any image, you can think of as a matrix. If you have any matrix, you can plot that as an image. Both ways it can be done, right? Okay, so fine. So let us look at a simple application of linear transformation. Let me open another worksheet. This is fine. Just a second. Is my second worksheet visible?
Yes, sir.
Okay, fine. So I was not sure. Okay, so let us look at how this linear transformation can transform any image, right? So as I said, digital image processing is actually and linear algebra go hand in hand, right? So let us start with a matrix. We'll again read the same image. We'll read the same image, and we can convert this into matrix. This I have already shown, so I'll not get into that. This is just a matrix, same matrix associated with this. So each entry in this matrix is actually a pixel, which runs from 0 to 255. That is what you see in this, right? So now you can plot this again. So this is a grayscale image. Now, if I take the transpose of this matrix, this is a matrix associated with the given linear transformation. If I simply take transpose of this matrix, the matrix we had, I've called that as image underscore matrix, and take transpose of this, and then if you plot, you will see that this image has become row has become column, column has become row, right? So if you compare with this, that is what you see, right? So row transpose, if you apply to a matrix, apply to an image, that is nothing but transpose of the matrix associated with that. Similarly, you can translate. So translation can be thought of as a matrix multiplication. So you multiply the matrix of the given image by this particular matrix. What is it? It is 1, 0, 100, 0, 1, 150. So on x-axis, we are adding 100, and on y-axis, we are adding 152. Z-axis is remain unchanged. So that is, if you do that and try to plot the graph, so it is just you are multiplying the matrix by this translation matrix. Translation is taken both along x-axis and y-axis, and that is what you see. You can see here x-axis is translated by 100 unit, y-axis is translated by 150 unit. So that is nothing but matrix multiplication. Or you can do scaling. If I scale x coordinate by 1.5 and y coordinate by let us say 1.8, and then look at what happens to the image. This is what you see here, right? This is scaling, right? Or I can do shear, right? That means you multiply the image by this particular matrix 1.5, 0, 0, 1, 0, 0, 0, 1, and then if you look at this, this is what happens, right? So it has applied shear along x-axis. You can apply shear along y-axis and then see what happens, right? So these are the transformations, simple transformations that you do to image. Or you can even reflect. That is nothing but multiply this image by this reflection matrix, -1, 0, and then reflection about y-axis I'm applying, right? And this the 2 cross 2 reflection matrix, along y-axis, the matrix is given by -1, 0, 0, 1, and that is what you see here. So this is reflection about y-axis, right? You can see here earlier the image was pointing to the left side, now it is pointing to the right hand side. So it has got reflection. If I reflect about x-axis, let me do that. I'll comment this out, then you will see that it's reflected about x-axis. Or you can even do rotations. Multiply this by matrix of rotation of cos of theta minus sine theta, cos theta, and to this matrix, this is what you're doing. This is rotation by an angle 20 degree. If I rotate it about, let us say about 10 degree, or let us say about minus 10 degree, then that is what you see, right? So all these transformation is nothing but simple linear transformation, nothing more than that, right? Of course, this Adobe can do several other things apart from this. So this is a simple application of linear transformation. So those who are teacher can give this as an application of linear transformation, right? Okay. Similarly, another thing, a simple entry by entry multiplication to an image has an application to what is called 2D convolution. That is a very, very important concept in machine learning and deep learning, convolution. Okay, so let me just what we mean by that. Let me just show you this GIF. So you can see here, think of this as this is a 5 by 5 matrix. On this, you are applying a convolution, and that is same as saying you are using some 3 by 3 kernel. And what is happening? You can see here. You just look at the first 3 cross 3 block. You apply this kernel. You then apply this 3 cross 3 matrix. So multiply each entry wise and add all of this together, and that is the first entry, 12.1. Right, 12.0 here. Then you move to this is so you can see from this what it means is that so this is the first, second, third, then fourth, fifth, sixth, seventh, eighth, and ninth. So that is why you get 3 cross 3 matrix. This concept is called convolution, and we are using here 3 by 3 kernel. Okay, and this has a lot of applications. Using this concept, you can do various other image processing. Okay, so and of course, there are some other concepts along with this, but this is one concept which is very, very frequently used in image processing. Lot of tools or algorithms are built on this concept. Okay, of course, they will be applying this convolution to very, very big matrix, and kernel size also will change and all that. So let me give you a few applications of this. So what do we do in the convolution? 2D convolution, and you can also do 3D convolution, especially if you want to deal with, let us say, videos. Then one uses 3D convolution, right? So what one does in this case is convert the image into grayscale image and obtain this as a matrix. And then actually what happens is sometimes you may have to add some zero at the edges. That is called padding. So you can appropriately you can use some padding and create sub matrices of all of these, and then apply this convolution matrix. That means look at this convolution matrix, apply this entry, multiply entry wise, and then add all of these together. Now, what is the input size and output size could be different. You can have a bigger input and getting smaller input. And once you have done this, then convert this into filtered matrix, and then see what happens to the actual image. So let us look at 1 or 2 examples for this. So again, I have taken this particular code. So for each step there is a inbuilt function. Don't worry about that, how it is written. Let me just run all these things, then we will look at a particular image. Okay, let me skip this example and directly let us go to this. Okay, so there is an image, lena.png. This is one of the standard images which is used for many of these kind of things. So you read this image and let us say apply identity kernel to this. So that is same as saying it will not do anything to the image. And if I apply to this, right? So again, you can see here, this is the kernel size. It creates a big giant matrix, and then it transforms into the output here. Input and output are of the same size. So that is why you need some padding, right? So this is original matrix. This is applied to this identity. So of course, it doesn't do anything to this image. Whereas if I go ahead and do some other kernel, if I apply this particular kernel, which is 3 cross 3, -1, -1, -1, -1, 8, -1, -1, -1, -1. This is this, and when we do that, let us see what do we get. Take So this is what it has done. This image has been transformed to this image. Now this is what is called edge detection. So you are detecting the edges basically from this grayscale image. That is what you see here. So this particular, so if I want to use edge detection, this is the matrix, this is the kernel, or this is what we have to do. Right. Okay, let us look at something. Another thing is sharpening the image. that can be done by taking this 3x3 matrix and applying convolution. So if I do that, this image will become a bit sharper. It's possible that you may not be able to notice while I'm sharing this image, but there is a glaring difference between this image, which is sharpened from this. Or if I use another, I can use 1 by 9 times 1, 1, 1, all these things. And then if you use this, the image will become some kind of blur image. That is what you can see here. This is a kind of blur image. Or you can use some other, there is something called Gaussian filter, or you can use some other kind of filter. You can use what is called embossing, or many others. Or you can use some arbitrary filter. Let us say I have used some identity minus 2 times Gaussian filter. And then in that case, this is what the image we get, right? And lots of, different kind of kernel you can search. And in fact, there are some standard kernel available. If you are able to come up with something new kernel, actually you can make millions of rupees like Adobe. Okay, so this is how this image processing is done. And as you can see here, it's a very simple application of matrix multiplication, linear transformation, and all that, right? Okay, so let me look at the other concept. So we have seen an application of linear transformation and entry-wise multiplication to image processing. Okay, right, and that's a very, very important kind of area in machine learning. A lot of people are doing this image processing. Okay, now let's look at another application. So all of you have been using this Google search, right? But have you ever wondered how does this Google search whatever the keyword that you give, right? And actually it was introduced by Sergey Brin and another Larry Page. Just give me a sorry, somebody was just knocking at the door. Okay, yeah, so how does this Google work? And that is very simple application of matrix multiplication, eigenvalues, eigenvectors that we study. So let us just look at how does this Google search work. So that is actually the initial page rank algorithm. And you can see here, based on this page rank algorithm, these two people, the Larry Page and Sergey Brin, actually they were graduate student at Stanford, and you see how much money they have made now, right? Yeah, so let us look at, so we'll think of, let us look at this image. Let me make it slightly smaller so that, yeah. So this, think of this as, let us say, how many? 10 websites. There are 10 websites and they are connected, right? So there are arrows. Arrows means there is a link, outgoing link, right? So if I'm searching some keyword, let us say artificial intelligence. So whatever is the website in which artificial intelligence occurs, there is the incoming link, right? So importance of any website is going to be the how many links or incoming links that it has, right? Based on any keyword, right? So so this is only 10 websites, but in actual principle, if you look at, for example, all of you can, since you are on the system, you can just look at how many active websites currently are there in the world. That will be almost maybe roughly about 200 million active websites are there. Okay, so if these many are active websites, and if you want to, so these websites, using this link, you can convert this into a matrix. Okay, so if there is a link from I to J, that you can put as a 1, otherwise 0. So if this particular set of website or link or internet links, we can generate a matrix in graph theory, what they call adjacency matrix. So this is a 10 cross 10 adjacency matrix. Okay, right. So you can look at, if there is a link from I to J, it will be 1, otherwise 0. Actually, in this case, J to I. If there is a link, for example, if you look at this particular entry, here index starts from 0. So this is a 0 means first website, 1 means second website. So if I look at this entry is 1, that means this entry is 2, 3. 3, 1. That means there is a link coming from 3 to 1. That's what you can see here. Okay, right. So once you have this matrix, adjacency matrix, now importance of each website can be decided by number of incoming links. So we can attach probability to each. So for example, if I look at first website, there are 8 incoming links. So the probability of reaching to that website will be 1 by 8. So so the same thing you can do with each column. So now you can divide each column by the number of 1. So first column, the entries are 0, 0, 1 by 8, 1 by 8, and so on. Right? So this gives you probability of hitting a particular website from a given. So if I look at, for example, this particular entry, if this lies in, let us say, 6th row and 5th column, that means 5 from website 5 to 6, the probability of that is 1 by 6. Right. So now suppose somebody starts surfing this particular network from website 3, 0, 0, so that we can think of as a vector 0, 0, 1, 0, 0, 0, 0. That is same as saying a person starts surfing this particular network from website 3. Right? Now from website 3, now if he, after one click, what are his probability of going into various websites? That is what we can find out. But that very simple mathematics or common sense will tell you that this is nothing but, look at this matrix multiplied by this vector. So if this matrix I have called as A, and this vector I have called as V0, then A times V0 will be a vector, and that will give me probability of each website, visiting each website after one click. So let us do that. If I multiply A times V0 and look at, I think something I did not execute this, A times V0, this is what you can see here. So this is probability on being first website is 20%, second website is 20%, and the last 4 is also 20%. Okay, that is what it last this on 7, 8, and 10 is 20%. Right? If I click once more, then how do I find out probability? That is nothing but multiply again that whatever vector you have got, multiply by A, that is nothing but A square V0. Right? So this is what you are going to get. Okay, and you can keep on doing after 2 clicks, after 20 clicks, what do we get? After 200 clicks, what do we get? And maybe after let us say 1000 click, this is what we get. So if you try to compare, for example, 200 clicks and after 1000 click, these are almost same, right? So if I do some more clicks, you will see that this particular vector is actually a fixed vector, and there is a theory behind this particular matrix. Turns out to be what is called a regular matrix, and for every regular matrix, if A is regular matrix, A to the power n will converge, and in this case it will converge to a fixed vector. That is what is called a stationary vector. Okay, so of course So that means in case we want to find this stationary vector, I need to find very large power of this matrix. Now, finding large power of a matrix is not an easy task, even for computer. But then here we are dealing with websites. So as I said, there are roughly about 200 million active websites. So that means if all websites are connected with each other, then that means we are dealing with 200 million by 200 million matrix. That is impossible to kind of multiply, take power. And when we want to find a higher power of that, what is the concept that comes to your mind? You have to use diagonalization, right? Diagonalization. If the matrix is diagonalizable, you can find any power very easily. But when you want to diagonalize the matrix, what is the concept you use? Eigenvalues and eigenvectors. So you need to study eigenvalues and eigenvectors. Okay, this is used in this particular one. But now if I have to find million by million matrix ka eigenvalue, eigenvector, that's again very, very difficult. You cannot do it explicitly, analytically. So you need to deal with these things numerically. And that is where numerical analysis comes into picture. Okay, so unless you can do this numerically, you will not be able to find, right? So all these concepts or algorithm of finding numerical eigenvalues becomes very important, right? So once you have got, for example, this is the vector, stationary vector. Now you can even rank, you can even rank this, and you can see here the second website has maximum rank. So that is the first website it will appear, followed by the 9th one, followed by the 4th one, and so on. Okay, so that was more or less the initial page, Google PageRank algorithm. Of course, there are various issues attached to it. There are possibilities that you get what is called dangling node. Then you also get you get to some website from where you cannot go to another website, or you can get into loop. All these things are dealt with in Google PageRank algorithm. They create what is called Google matrix, and through that they try to kind of resolve this issue. Okay, so and that roughly what it means is you take this matrix and think of a website in which everything is connected to everything, and then take some kind of convex linear combination of this matrix which we define, followed by 1 minus alpha times this S matrix, which is 1 by n times all entries are 1 by n, where n is the size of the network. Okay, so that is what is called Google matrix, and it turns out that this is also stochastic matrix. And of course, this alpha is called damping factor. There is a reason why they use 0.85. After simulation, they have found out that this works quite well. Okay, so that is how it works. Okay, of course, here in this case, there is no diagonaling node or any loop, so we don't have to create Google matrix, but you can do. Okay, so that is how very basic Google search work, right? So as soon as you search any link, any keyword, it will of course you can look at Google and then see how does this search work, what is the actual thing it does. Okay, but it gives you all these results in very, very quick time. That it doesn't mean that it goes to all the website and searches the keyword and then only collects the information. That will take a lot of time. So Google has a lot of servers placed all around the world, and these servers keep on working, keep on collecting the information. So as soon as we search this keyword, it goes to this server, not all over the place. Okay, right. So I mean, one can talk hours on this. So this is one very simple application of Google, how this Google search works. And actually, this is a forecasting problem. So you are forecasting in long run, where will a particular person be on which website. So this is a forecasting problem. So many forecasting problem can be thought of as an application of this, right? As an application of matrix multiplication, of finding large power, right? For example, migration problem, or even the weather forecast, right? All these things can be thought of as an application to this. Okay, let's move on to another application of eigenvalues, eigenvector, and this is called singular value decomposition. So singular value decomposition is very, very important concept in linear algebra, having tons of applications. In fact, if you know singular value decomposition of any matrix, then you know a lot of things about that matrix. So let me just briefly look at how this can be used for what is called image compression. That again is a tool which you keep using. Many times your data is very huge, your image size is very, very huge. And if you want to send this information, then you need to compress and then send it. Okay, so what is the idea behind the image compression? So one of the way it can be done, image compression can be done, is using what is called singular value decomposition. So let me very briefly explain what is the singular value decomposition. So if you have any matrix, M cross N matrix, need not be square matrix, any matrix, you can split this matrix into U times sigma times V transpose, where U and V are orthogonal matrices and sigma is a diagonal matrix like this, where this is diagonal entries, these are all zeros. And if the matrix rank is R, you will get R cross R, this matrix, and these are all zeros. You can think of as column vector U1, U2, UM, and V can be thought of as column vector V1, V2, V. So a matrix is orthogonal each and if and only if the columns are orthogonal and so on. Right. So that is what is called singular value decomposition. And proving this result is utterly trivial. You can look at any standard linear algebra text, you will see that. And it has lots of applications. Okay, so let us look at one such application. Before we look at that application, let us look at this particular decomposition. We can write U as U1, U2, UN, V as V1, V2, Vn, and then this A can be written as sigma 1 times U1, V1 transpose, sigma 2 times U2, V2 transpose, plus dot order sigma. The last one should be sigma R times UR, VR transpose. There is a typo. Okay, and here this sigma 1, sigma 2, sigma R are arranged according to decreasing order, and they are all non-negative. There is a reason behind why it is non-negative. So actually, if you look at this, each of this term in this sum, that is a rank 1 matrix actually. This U1 and V1 are vectors, so the product will be of rank 1. So the matrix A has been split into rank 1 matrices. And sigma 1 is very large, followed by sigma 2. Towards the end, this will be very, very small. So most of the information will be there in the first few terms. The remaining, for example, sigma R could be very, very small, 0.00001. And then when we multiply by that to any matrix, that entry will become very, very small. So that is not going to give me a lot of information. So we can ignore last few terms, right? And first few terms itself will give me most of the information about the matrix. And that can be applied to an image. Now think of an image, convert that into a matrix, take the singular value decomposition, take first few terms, and that will give you most of the information. So as a result, suppose from satellite, if they want to send a picture to the ground, instead of sending the big high quality image, they can compress and send it, because sending is a task, right? It is time consuming. So let us look at how we can make use of it. So again, let us read an image. In this case, I have read an image called tiger. So this is image of a tiger. Let me show you. Okay, and we have converted. Let us look at the size of this image. This is already in 2x2 two-dimensional array. This is 1200 cross 719, and then first convert this into gray image, because we will be of course you can do singular value decomposition to the image, to the color image also. In any image can be split into what is called red, green, blue channel, and one can apply SVD to each channel and then combine. Right. So then you can make this into a matrix, and this is just a grayscale image. Right. Now what do? We will find out singular value decomposition of this particular matrix, that is this particular image. So the first one is stored in U, then in S, and then BT. And after that, let us plot only first 5 components of this decomposition, then 10 components, then 50 components, 100 components, 200 components. Remember, the size of the matrix is 719. So most likely this rank of this particular matrix will be 719. So let us plot this one. So what we are doing is we are actually taking only first R cross R or R term. So in this case, 5 terms, 10 terms, 50 terms, 100 terms, 200 terms, and let us plot all these things together. So you can see here, when I take only first 5 terms, the image is not very clear. You can, I don't think we can make out that this is the image of tiger, right? But if I take 10 terms, first 10 terms, you can see almost it's quite clear that this is a tiger. If I take 50 terms, this is as good as kind of original, not very, quite good, right? If I take 100 terms, even better. 200 terms, it's almost like original. So out of 719, we have taken only first 200 terms, and we are getting most of the information. So that actually this has compressed the image. If you look at the total size of this or the size or the amount of data that is required compared to the original, that will be significantly small. So that is what is called image processing or image compression, and we are using singular value decomposition. That is a very simple application of these two image processing, namely image compression. In fact, singular value decomposition. So here what we have done is we have got rid of some of the parameters, right? This is also known as in machine learning an algorithm called dimensionality reduction. Okay, so we are reducing the dimension. So earlier it was 719 cross 719, those many parameters, out of which now only 200 parameters is giving me good information. Another very, very similar concept in linear algebra is called principal component analysis. And principal component analysis and singular value decomposition are very, very close to each other. They are quite related to each other. And they are extensively used in machine learning algorithm as a tool, which is called dimensionality reduction. Okay, so many data has a lot of parameters, out of which if you want to take only those parameters which are significant, then one can use this particular tool. Okay, now let's look at one more application. Can I take another 5 minutes? Yeah, okay. So, right. So let us look at another application. Say this is an application of orthogonal projection, which you study in inner product space, orthogonal projection. So that can be used in what is called least square methods. In statistics, they call this as linear regression or multilinear regression, linear, multilinear, non-linear regression. That is same as you build certain model and fit to the data. Okay, and based on the model that you have fitted, you can predict what is going to be the output given the inputs. Okay, so for example, you can fit a straight line, you can fit a plane, you can fit any polynomial. Curve fitting, another term for this, and that is nothing but simple linear algebra, period. Okay, it's a very simple concept of linear algebra. Okay, so instead of looking at a simple data, I have looked at, let us look at this particular data. This is the set of data points that we have. Okay, and to this data, if I look at this data, it looks like these points are in circle, right? So most likely we can fit a circle to this data, or what is a circle that will be best fit to this data. That is the problem. So this problem can be converted into optimization problem. It can be converted into linear algebra problem or coming from the statistics. Okay, right. So what do we do? Let us look at how we can deal with this problem. So suppose we think of that the best fit circle to this particular data is going to be circle centered at AB with radius capital R. Okay, so that is the circle you want to fit into this. So that is same as saying you want to find the parameters A, B, and capital R, which are the unknowns, which is the best fit to this data. Now, you have to ask what is meaning of best fit. So best fit meaning, if you look at any of this data point, look at its distance from this particular circle, that should be small. And that should be true for each and every point. So that distance or mod of the distance can be thought of as error. So all you are doing is you have to minimize all these error. That is same as saying, look at, so if I look at ijth point, if I look at ith point, xi, yi, the point, the corresponding value is going to be this, the error from this is going to be this, that is R square is, if it will bear on the circle, this is going to be R square. So that difference is going to be the error. So you minimize the sum of the error square. So that can be thought of as a function of three variables A, B, and R. And this is what you get. So this is sum of the error square. And that very easily you can convert into a matrix equation. You can think of this as this sum of R square. This is actually sum of R square as norm of A theta minus Z the whole square, where R is Ri is equal to this. So sum of the R, there is a typo here, sum of R square will be this matrix, where what is A? A is this matrix. First column is 2x1, 2x2, dot, 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 2xn. Second column is, so the twice coefficient of y. Third column is all 1, 1, 1. This theta, that's a unknown, is a vector A, B, C, and R square minus A square, B square. And this Z, which is the right hand side, is x1 square plus y1 square, and so on. Okay, so now this problem is actually to find theta, which minimizes AZ minus theta. Now, how do we think of this problem into linear algebra problem? So actually, if you look at A, here A is going to be n cross 3 matrix, n rows and 3 columns. So the n rows 3 column matrix, that can be thought of as a linear transformation from R3 to Rn, R capital N. Okay, and this Z, if you look at, Z is a point in R capital N. So the theta is such that A theta is going to lie in the image of A. That is a subspace. So if you look at this vector Z, if it lies in the image, it will be 0. If it doesn't lie, then you can look at what is the smallest distance of Z from the image space AZ. And that smallest distance is nothing but orthogonal projection of Z onto the image space, which is a subspace of the matrix A. So that is, so the solution of this, which can be obtained using what is called least square method using calculus or using linear algebra, this is nothing but the orthogonal projection, right? And it turns out that the solution of this is theta star is equal to A transpose A, the inverse of that times A transpose Z, that is called least square solution, and the A star theta is going to be the orthogonal projection. Okay, so that is a very simple application of orthogonal projection to what is called best fit problem or fitting curve problem. This is actually non-linear, but it has been converted into linear regression problem. Now let us look at how we can do this. So I have generated some set of points and I have plotted them. Okay, so these are the set of points here. Now you can see here I have converted this x and y and then created a matrix A whose first column is 2x, second column is 2y, and last column is all 1, 1, 1. And then we are looking at the vector z. This is the vector z. And after that, we can find theta, which is A transpose A, inverse of that times A transpose Z, and then find out. So once you have got theta, then you can find out A, B, and R. And once you have that, these are the solutions. So A approximate value is 2.963, B approximate value of B is 2.523, and C is 1.987. So that is so this is the radius, roughly about 2. This is 3, 2 is the center, roughly 3, 2.5 is roughly. Of course, there will be error, and then we can even plot the set of points along with the circle that we have fitted. Okay, so we are able to fit this circle. That is nothing but using what is called the orthogonal projection. So this is again very simple application of inner product orthogonal projection to what is called broadly least square problems. This is very, very commonly used algorithm of least square in machine learning and data science. Any data when you have, if you want to fit some kind of model, this is what we use is regression. There are various kinds of regression: linear regression, non-linear regression. There are also other kinds of regression. So those of you who are interested, you can look into these things. Of course, I can talk about many other applications, but since it's already I have exceeded the stipulated time, I'll stop here. But there are many applications, and all these are heavily used in machine learning algorithm, artificial intelligence, and they are very simple application of linear algebra. Nothing more than that. Okay. So thank you very much. In case you have some questions, you can let me know.
Thank you, Dr. Ajit Kumar, for such an informative and interesting talk, underscoring the applications of linear algebra to machine learning and artificial intelligence. Now the floor is open for questions, queries. So one of our participants, Akshay, wants to know if we want to improve picture quality of blurred image for real life application use, can we improve it?
Yes, that is again some you will see that there are kernels which can sharpen the image, right? So you can use. I took only few examples from that, but actually you can, if you look at, for example, Python, there is OpenCV package which deals with image processing, and behind the scene, of course, there is a linear algebra, but there are you can use inbuilt packages and you can improve the quality. All of these image processing can be done, including actually locating some object from some picture, etc. All these things are part of what is called convolution.
Thank you. Second question is, if artificial intelligence is trying to mimic human brain, then won't the neurologist have the edge over the people knowing linear algebra or other mathematicians?
Yes, in fact, that's correct. In case you know those who have these kind of background, they will have the edge in the sense that you can actually understand what exactly is happening behind the scene, right? Not only that, you can create different. For example, you can find your own kernel, and then which may do something much better than the existing algorithms, right? And in that case, you are going to make money, right? So all these the process people have developed, that is actually it also has error, right? So in case you can find out some kernel which can do much better than the existing one for sharpening the image or for edge detection or for some other purpose, that way you can make money also. right? So how much money you can imagine how much money Adobe has made. I think they introduced this software in some 1988, 87, and since then must have made millions of dollars, no? Right.
So students wants to ask about the package. You told us we can improve the blurred picture using it. So they want to know about which package they should go for.
So one can use, there are, as I already said, in Python, which is open, free and programming language, which has lots of library. One of them is called OpenCV, which exclusively deals with image processing. So you can explore that that package, OpenCV. And there are many more.
Okay. Another question is, majority of times there are many softwares which uses present picture of a person and which we give as an input, and they give as output of an old aged person. So what kind of linear transformation is done here?
Yeah. Right. Yes. Yeah. So these are all linear transformation, as I said. Actually, you can. I'll tell you, those who are student or even teacher, there is a book by Harvard Anton. It has a chapter of applications of linear algebra, some 20 applications, and one of the chapter deals with how you can transform one image to another image, including if I give my image, it will tell me how will I look after 80 years or somebody else picture. So you just look at that book, and another book you can look at. Actually, it's a freely available. It's called 31 Miniatures of Linear Algebra. So that has some 31 very simple applications, 31 miniatures in linear algebra. Okay, right.
Thank you, sir. Another question is from Deepak Bakal. Can you suggest some reference on says math for algebraic coding theory?
Coding says math. There is a book by one Australian mathematician. I think it is called, I forgot the name of but there is a book on coding theory using Sage math. There is a book, I forgot the author's name, but if you send me an email, I can.
Sure, sir. Sure, sir. So so I think we are short of time. So I think Anil, I shall wind up now.
Yes, ma'am. Yes, you can proceed.
Okay. It's my privilege to have been asked to propose a vote of thanks on this occasion. I, on behalf of Department of Mathematics, Atmaram Sanatan Dharm College, extend a very heartfelt gratitude to the esteemed speaker for sharing a very insightful webinar underscoring the applications of linear algebra to machine learning and artificial intelligence. Sir, you have explained it using very simple examples, like if we have you took an example, if we have an image, we can think of a matrix, and if we have a matrix, we can think of an image. You explained this using beautiful example of Statue of Liberty. Further, you explained this using picture of tiger and so on. So I take this opportunity to extend our most sincere thanks to all our participants. I want to extend my thanks to our dynamic principal, Professor Gyanatosh Kumar Jha, for always extending his kind support. I am also thankful to the organizing members of the webinar committee, Faculty of Mathematics, for their efforts and kind cooperation. Thanks a lot, everyone. This was indeed very interesting lecture followed by a very healthy discussion. But due to the time constraint, we'll have to stop here only. Stay safe, stay healthy. Thanks a lot, everyone. Thank you, sir.
Thank you. Thank you.
Thank you so much, sir. Thank you.
Yeah, my pleasure. And good night to everybody. Thanks a lot for attending.
Thank you.
Good night, sir.
Bye. Good night.